So I think everyone knows why it'd be good to be able to test year round, especially sort of in terms of commercial building testing, like extending the season so they can look throughout the year. And also, in theory, in warmer times of year, there should be fewer uncertainties from party wall heat transfer and heating system performances, because you shouldn't be using the heating. And presumably all the buildings will just be free floating to external temperature. So today I'm just going to run through some results from 3 case study houses. Very brief Bayesian recap just to explain what some of the numbers mean at the end. And I'll show you the results, see which models work best for what houses, how they compare to co-heating tests, and yeah, what to do. Shiny results. So these are the 3 houses. They're quite different. So house A is occupied and newly retrofitted, semi-detached. But yeah, there are quite a lot of issues with their heating system and things, so the data you can get is quite patchy. The house B has got loads of glazing on one side, not the side pictured, but it's got even more on the other side. Skylights and things. It wasn't permanently occupied, but it was heated, and there was electricity used going around and looking at it. House B is mid-terrace and occupied, so obviously a little bit more complicated, but we do have temperature measurements from the houses either side. Wow. So there's lots of tests in this slide. I'm just going to wait a little bit. So all of these are analysed using Bayesian statistics, which means I'm not getting point estimates of HTCs or any of the parameters. I'm getting distributions of the parameters. Those are my estimates. So everything I'm quoting is just the median and then the standard deviation of these widths. So they're not full uncertainties. They assume the model is correct, and it's just about how certain you are about the value of that parameter given the model and the data. So that's why they might look a bit odd. So the first model is looking at sort of a dynamic method of incorporating solar gains into a sort of standard thermal capacitance model. So here, rather than just having sort of one solar input, you have one for diffuse solar radiation and then a separate one per sort of glazed facade of the house. So you can obviously adjust that, or if you don't know the orientation of the house or you don't know what facades are glazed, you can just put, and hope for the best. That's some results from house A in February and in June. So here you've got just lists of models for each of them, and so if you look at the sort of number of S's at the end, or whether or not there's a D there, that's the diffuse input, you can see that in winter, it really doesn't matter how many different facades you include. There's very little difference in the internal temperature prediction, which you'd expect. Solar gains are going to be less important there. There's more variation between the different lines from the June data, but you don't actually need all 3 glazed facades for this one. The model that was selected as the best representation is the one only including 2 of the 3. So this is house B, which has skylights and sort of a winter garden and loads of glazing. And for this one, for both January and April, only one facade was needed to accurately represent the internal temperature. But in January, diffuse radiation was also required, which makes sense. It was probably cloudier than in April. Moving on to the next model. So this is about incorporating party wall heat transfer. So as well as sort of this bit of the model on the right, which in the previous bit, you've also got an extra thermal resistance of the party wall and then the temperature next door. And obviously for the mid-terrace house, you have an extra one of those as well. So for this is house A, which is semi-detached, and we didn't know the temperature next door. So here it's just assumed to be 17.5 degrees throughout. And so here is actually slightly different data to I showed you before. This is from November, and the house was unoccupied for this week. So you can see the blue and the red lines where it's just there's no sort of party wall heat transfer included. They miss the mark quite a bit. But the green and yellow lines, once you're including that party wall heat transfer, which is obviously going to be dominating when they're away in winter, it proves the model quite a lot. But now this is back to February, so occupied in winter. And you can see it does still matter, but not nearly as much. The partial heat transfer here. And in June data, if the partial heat transfer doesn't really change, it's the solar being included or not that really makes a big difference to the accuracy of the internal temperature predictions. So this is LC, the mid-terrace one. You can see here that actually it's the part, including the two-party walls, is really important in both January and July. It's more important in January, with the solar still being important in July, but it's really sort of crucial throughout the year for this. So house dependent, I think, expect. Last of the three models is one including sort of radiative heat losses. So this would be to clear skies overnight. And so we've got a term there, including the effective sky temperature, which was determined empirically. And the A is a parameter to be estimated as the product of the emitting area and the emissivity. And it's just the 7 volts constant in there. So it's treating the house as sort of flat body. And you see this this model edition, so it's the ones with the 1L on the end. These have less of an impact than any of the other two model I've shown here, but it is still crucial for this house. It still makes a difference. See, you know, for this house in the winter, this is the one, the mid-terrace one. It's still really just mainly important to have the neighbours in there. But in summer, sort of got, you know, the one with neighbours and the radiative heat loss is the one in the middle. So it's closest. The other two are wrong in different directions. Too much heat gain and too much heat losses. So here are the, I put HPLC here rather than HTC because I've not taken into account the boiler efficiency in these models. So you can see that it is possible to get reasonable seeming results with summer data as well as winter data compared to the coheating tests. For most houses, you'll notice the humongous standard deviation for house C in July. So for most houses, it is as much as you can say here. And also it seems that errors do seem to be larger in the summer.
What's it, 2 minutes?
Good, so I'm on this slide now. So yeah, it seems that summary sort of dynamic cheaper solar gains seems quite important, but you don't, and it's also allows you to sort of simplify the model or highlight dominant facades or insignificant facades in terms of solar gains. Partial heat transfer can be really crucial, but obviously this house depends on. If anyone's interested, I can show you the full set of results for these models. And for house C, often if you included the neighbours, you got a beautiful internal temperature prediction. The HTC was about 30 because of the way the model had optimised it. It just assumed that they were controlling the entire temperature with that. So it's something to be careful about. And the radiative heat losses weren't often significant across the houses, but sometimes they helped the HTC get much closer to the coheating result. So yeah, HTC can be calculated with summer data. I think that, but there's a lot more to be done sometimes. It's job.
Frances? That's fine.
Extend the screen.